Quark-Gluon Plasma, the universe's hottest particle soup. Imagine a state of matter so extreme, so energetic, that the very building blocks of reality are liberated. This is the Quark-Gluon Plasma, or QGP. It's not your everyday solid, liquid, or gas. QGP is an extreme state of matter where quarks and gluons, normally confined within composite particles, are set free. This exotic plasma existed in the first few microseconds after the Big Bang. By recreating and studying QGP, we gain invaluable insights into the fundamental particles and forces that govern our universe. It's a journey back to the dawn of time, one collision at a time. To understand QGP, we must first delve into the standard model of particle physics. This model describes the fundamental particles and forces that make up all matter. Matter is composed of two primary types of fundamental particles, quarks and leptons. Leptons include electrons and neutrinos, while quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Quarks don't exist in isolation under normal conditions. They combine to form composite particles called hadrons, such as protons and neutrons. Protons and neutrons, in turn, make up the nuclei of atoms. These nuclei, surrounded by electrons, form the atoms that constitute all the matter we see around us. The force that binds quarks together within hadrons is the strong force. It's the most powerful of the 4 fundamental forces: dwarfing gravity, electromagnetism, and the weak force at short distances. The strong force is mediated by particles called gluons. Gluons act as the glue that holds quarks together, constantly exchanged between them. Under normal conditions, quarks are confined within hadrons. This phenomenon is known as quark confinement. However, under extreme conditions of high temperature and density, the strong force weakens. This weakening allows quarks to break free from their confinement. When the temperature reaches trillions of degrees Celsius, a phase transition occurs. Quarks and gluons are liberated from their hadronic prisons. This leads to the emergence of the Quark-Gluon Plasma. Quarks and gluons exist as a deconfined, interacting soup. Since QGP existed only in the early universe, we can't simply observe it directly. Instead, we must recreate it in the laboratory. The primary method for creating QGP is colliding heavy ions, such as gold or lead nuclei, at near light speed. These collisions generate the extreme temperatures and densities required for deconfinement. 2 major facilities are at the forefront of QGP research: the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Laboratory in the United States. The Large Hadron Collider, or LHC, at CERN in Switzerland also plays a crucial role. Both facilities accelerate heavy ions to incredible speeds and smash them together. These collisions generate temperatures exceeding trillions of degrees Celsius. That's far hotter than the core of the sun. The Quark-Gluon Plasma is incredibly short-lived, existing for only a fleeting fraction of a second. This makes studying its properties a significant challenge. Scientists analyze the particles that emerge from these collisions. They look for specific signatures that indicate the formation and properties of QGP. One key signature is the suppression of certain particle production. This suppression occurs because quarks and gluons lose energy as they traverse the dense plasma. Another signature is the flow patterns of emitted particles. These patterns reveal information about the collective behavior of the plasma. The behavior of jets, collimated sprays of particles as they traverse the plasma, also provides valuable insights. The jets interact with the QGP, losing energy and modifying their structure. QGP exhibits fluid-like behavior, flowing with minimal resistance. It behaves like a nearly perfect fluid. This perfect fluid behavior is characterized by extremely low viscosity. Viscosity is a measure of a fluid's resistance to flow. Despite the deconfinement of quarks and gluons, the strong force still plays a crucial role in their interactions within the plasma. It dictates how these particles interact and influence the overall behavior of the QGP. Studying QGP helps us understand the evolution of the early universe. It provides a window into the conditions that existed shortly after the Big Bang. QGP research also sheds light on the formation of hadrons. It helps us understand how quarks and gluons eventually recombine to form protons, neutrons, and other composite particles. The study of Quark-Gluon Plasma is a complex and ongoing endeavor. It requires cutting-edge technology and sophisticated theoretical models. Researchers hope to unlock further secrets about the universe. They aim to understand the fundamental nature of matter and the forces that govern it. QGP offers a glimpse into the universe's fiery past. It allows us to probe the conditions that existed at the very beginning of time.